Welcome back to Polymeric Biomaterials. We are still looking at the theme of biomedical polymers, and as part of the last lecture under this theme, we're today going to be focusing on one very important class of biomedical polymers that are widely used in the clinic and also in research, namely hydrogels. And in today's lecture, we're going to be focusing on first starting off with a physical picture of what a hydrogel is and look at the classifications of hydrogels. Then we will briefly look at some important hydrogel preparation methods, and then we will turn our attention to the thermodynamic aspects of hydrogel swelling. So these are gels that can swell in the presence of water, and there are thermodynamic aspects associated with it. So we will recall some of our earlier discussions on Flory-Rehner and see how those can be related to hydrogel swelling, and then we will look at a very important equation, the Flory-Rehner Merrill-Peppas equation, that is used to describe a very important structural parameter in hydrogels and can relate that structural parameter to swelling behavior. And then, as always, we will take a brief look at process property performance relationships, as we have seen with both synthetic and natural biomedical polymers earlier. And then towards the end, we will look at some advanced stimuli-responsive types of behavior that hydrogels can undergo, which can be used in different kinds of biomedical applications. Now, hydrogels are a very involved and a very complicated, complex topic. What we can do in a lecture like this as part of this course is to look at some important concepts guiding hydrogel design and performance. And as always, the hope is if you are able to appreciate and understand some of these concepts, you can always contextualize them whenever you come across newer preparation methods or newer applications, etc. in the future. So with that caveat in mind, let's jump right into the lecture today. So we'll first start by looking at the physical picture of a hydrogel. So hydrogels, as the name itself should indicate, are gel-like structures that can swell in the presence of water. So these are gels that are covalently cross-linked, which is the first important criterion for a hydrogel. Second is they can swell in water. Now, if you can recall some of our earlier discussions in polymer architecture, where we've looked at elastomers, that would be very useful here, where you will be able to recall that lightly cross-linked networks provide elastomer-like properties to polymers, and that's what we are looking at here. So these are covalently cross-linked, but cross-linked just enough to not make them extremely stiff and rigid, cross-linked just enough such that they now have elastomer-like properties in the network, and because they are cross-linked, they will not dissolve in water, they will only swell in water. And another example that we have briefly alluded to earlier is the presence of sodium polyacrylate in baby diapers, where the idea is very similar. The liquid that comes out has to be absorbed by the diaper, and the polymer present inside the diaper will take up the liquid, form a gel and keep swelling without releasing the liquid but also not dissolving. So if you ever get a chance, try and see if you can take apart a baby diaper, take out the material inside and try and test out how it interacts with water. It's an interesting exercise. So coming back to now hydrogels, what we are essentially talking about is two things. One is a covalently cross-linked network which resists dissolution, and the second is the ability of these chains to undergo favorable interactions in the presence of a particular solvent. In this case, because it's a hydrogel, it is water, and they can absorb a large amount of water. 90+% of hydrogels can just be water, and if the water absorbing capacity is extremely high, sometimes they are called super absorbent materials or gels. Now, the fact that they are covalently cross-linked doesn't mean you can't have other types of interactions or even other types of ways to prepare hydrogels. For example, you can also have ionically cross-linked hydrogels, where we have seen earlier that if you have polymeric chains, natural polymers particularly, that are positively or negatively charged, those can be cross-linked across the chains through the use of the oppositely charged species, right. You can also have hydrogen bonds and hydrophobic interactions that also lead to gel-like behavior, and of course physical entanglements as well. But typically when we refer to a cross-linked hydrogel network, we are typically referring to a covalently cross-linked network, although we will still look at examples of some of these interactions as part of this lecture. One other important aspect to note with hydrogels is the interactions between the chains. Like we have said, one chain can connect to the other through these covalent attachments, which is very different from linear or branched polymers, where the interactions across chains are typically secondary interactions or non-covalent interactions, such as hydrogen bonding, van der Waals forces, hydrophobic interactions, etc. Now, this cross-link or the junction points between two chains, one example of that could be you can have bi or tri or even tetra-functional covalent junctions. So, you can now imagine a chain like this or a network like this, where each of these points represents a covalently cross-linked junction, right. And depending on the type of curing or the cross-linking that is done for the chain, you can have either a bi or a tri or a tetra-functional cross-linker that leads to these junctions. But in reality, what you will notice is you will always have non-idealities, such as these. Including unreacted functional groups that have not functionalized. So, you see this dangling end here that is not cross-linked anywhere. You can also have loop-like structures such as shown here, and it so happens that these will not directly contribute to the elastomeric properties of the network, and that is an important point to note, because as we will see later, this will affect how the hydrogel swells in the presence of water, and as we will see later, the Merrill-Peppas equation will account for some of these non-idealities, and these do possess a finite size, these junctions, and contribute to the physical properties of the network. Primarily, one important point that we are focusing on here is swelling. So, with that stage being set, we are now in a good position to look at some classifications of hydrogels based on different categories. If you think of the method of preparation, for example, you can have homopolymer or copolymer or interpenetrating networks. Now, homopolymer, as the name should indicate, consists of a single monomeric unit that is now cross-linked. You can have copolymeric hydrogels also, depending on the choice of monomers. As we will see in just a bit, you can also have what is called an interpenetrating network. So, these are two different networks that are intertwined with each other, and the two networks have different monomers, may or may not have different monomers, but typically have different monomers. You can also have physical hydrogels, where the interactions between the chains are not necessarily covalent. As we have just seen, there could also be other types of non-covalent interactions, such as hydrophobic interactions. You can have hydrogen bonds stabilizing some of these chains, which also results in gelation. You can also have van der Waals forces, chain physical entanglements. All these factors can contribute to what you would call physical hydrogels. Now, these interactions, it turns out, are very important for the reversibility of the gelation process. Now, as you can very easily imagine, these covalently cross-linked networks that we have looked at here, once they are cured and formed, you can't take them back to the uncross-linked state. That is not going to be easy, because they are covalent cross-links. Whereas, in many cases, when you have physically driven gelation in some of these hydrogels, some examples of which we will definitely see, then you can take it back to the sol state. So, these are what you would think of as what can undergo a sol to gel transition, for example, in the presence of heat, but you can also take it back to the solid state if you remove and reverse the Q. So, there's a specific Q such as temperature that's going to lead to a sol-gel transition, and once you remove the Q, they can go back. This is very different from the covalently cross-linked networks that we have just seen. You can also have hydrogel classified based on the presence or absence of charge. And you can have neutral hydrogels. Many of the hydrogels that are popularly used are neutral. You can also have anionic or cationic hydrogels. A good example of an anionic hydrogel would be something based on alginate, which is a polymer that we've had a chance to see in some detail in the previous lecture, lecture number 20, as also chitosan for cationic hydrogels. Again, this is something that we've had a chance to see in the previous lecture, lecture number 20. Of course, you can have ampholytic hydrogels. Protein-based hydrogels, for example, would fall under this class. You can also have other types of hydrogels based on DNA, for example, where you use the base pairing rules which are largely governed by hydrogen bonding to form networks. So, you see the template or the canvas is pretty large, where you can now choose a large number of different monomers based on their properties and use them depending on the application. Of course, you can also have degradability as one way to classify hydrogels, and you can have hydrogels that undergo ion exchange and sort of dissolve, where the cross links just come apart, and one good example of that would be alginate. You can also have hydrolytic and enzymatic degradation, where the backbone or the cross links can undergo chain scission, some of which become important, as we will see later in this lecture, for the control release of biological molecules in the presence of certain triggers. So, we will look at those things towards the end of this lecture. So, with that being said, we can now look at some ways to prepare hydrogels, and this is a very limited subset that we are going to cover. We are going to look at a snapshot of some types of hydrogel preparation methods. Of course, like I said, the number of preparation methods is extremely large. You can have very many varieties, but what we are trying to do here is to look at it from a conceptual perspective and ask what are the interactions governing the hydrogel network and how is the network formed itself. One way to prepare hydrogels, for example, is to have bifunctional polymer with reactive N groups or a multifunctional polymer with reactive pentant groups. So, you can imagine now that a bifunctional polymer with reactive N groups, one example of that we have seen earlier is PEG diacrylate. The diacrylate group can now photopolymerize in the presence of free radicals and the presence of UV light to form a cross-link network, and the acrylate groups at the end that stick out would be one good example of this bifunctional polymer with reactive N groups. By the way, the diacrylate functionality is not restricted just to PEG, although that is what we have seen quite a bit in this course. You can also have something like gelatin methacrylate. Gelatin is another important polymer that's a denatured form of collagen, and being a protein, it has its own utility in biomedical applications, and if it is methacrylate functionalized, again it can undergo photopolymerization to form a hydrogel. So, what's important here is not to get stuck with either gelatin or PEG, but to note the fact that the diacrylate here and the methacrylate here are the important functionalities. So, you have to be able to connect the structure, the presence of the acrylate group to the ability to form a cross-link network because of the presence of the functionality. So, you can now imagine that if you, for example, zap this with UV light of a specific wavelength, it is going to form a cross-linked hydrogel network. So, that is one way to make hydrogels. You can also have something called an interpenetrating network, as we saw on the previous slide. So, here what happens is when you want to have two different groups or two different chains that can form the network, what typically you can do is you first formed one hydrogel network as shown here. Then what you do is you swell this hydrogel network in a solution containing monomer 2 for a different network. So, you have made a network, and the network, after curing or after cross-linking, you are now swelling it. Now, the solution that in which it is being swelled has the monomer for the second network. Thereafter, you polymerize monomer 2 in the hydrogel network 1. That is going to lead to this interlaced or interwoven kind of a structure called an interpenetrating network or IPN, which has a lot of important applications in biomedical engineering, particularly tissue engineering and controlled drug delivery. So, this is another way to make hydrogels. An ionic example would be to look at, for example, a polyanion, right, like alginate for example, where you have these negative charges present throughout the chain, and there are potentially at least two ways in which you can cross-link them. One is to use a multivalent cation, and can you recall what cation is popularly used for alginate cross-linking? If you are able to recall, you will know that it is the calcium divalent cation that cross-links the polyanion, which is the alginate chain, or you can also have through another route use a polycation like chitosan, which is positively charged to form a structure that looks like this. So, in the former case, you would obtain what you would call an ionotropic cross-linking hydrogel. In the latter case, you would get something called a polyelectrolyte complex, and the polyelectrolyte complex should be fairly intuitive to appreciate, because you have two different chains with two different or oppositely charged species now interacting together to form this complex. So, that is another way to make hydrogels. That is a good segue for us now to look at some examples of physically driven gelation methods, and two important examples are HPMC and agarose. Now, HPMC is a polymer, hydroxypropyl methyl cellulose is a polymer that we have again looked at in the previous lecture, which is derived from cellulose through substituents. And interestingly, both HPMC and agarose, the gelation is driven by temperature. So, they undergo the sol-gel transition due to temperature driven effects. In the case of HPMC, what you have is you have these hydroxyl groups at room temperature that can very strongly hydrogen bond with water. So, they are soluble, unlike cellulose, which is not soluble. So, at room temperature, HPMC is soluble in water because of the strong hydrogen bonding with the hydroxyl groups. But as you heat, the heat supplied, that energy can now break apart these hydrogen bonds, and remember, in HPMC you also have these methoxy groups. So, at higher temperatures, because of the absence of hydrogen bonds stabilizing the polymer solvent interactions, you now start seeing that the methoxy group interactions start dominating at higher temperatures. So, the hydrophobic associations between methoxy groups leads to gelation at higher temperatures. So, the sequence of arguments should be very clear and is as follows. You are looking at hydrogen bonded solubility at room temperature, and as you heat, the sol undergoes a gel transition because the hydrogen bonds are now disrupted, and now the hydrophobic associations between the methoxy groups become important, leading to a fibrillar like arrangement leading to gelation. In agarose, it is sort of the opposite. What you will see is once you have heated the agarose solution, it becomes a sol, and in that heated state, the agarose exists as random coils, and as you cool down, hydrogen bonds start stabilizing the chains, leading to what you would call a double helix formation, which leads to aggregation of these different units leading to gelation. So, again you have to be able to relate temperature to random coils at high temperatures where it is fully soluble, the agarose is fully soluble in water, and as you cool down, you can start to get some kind of self-assembly through this double helix formation stabilized by hydrogen bonds, which leads to gelation as you cool it down below 40 degrees. So, these are two very nice examples of physically driven gelation methods, and as should be quite obvious, both of these are reversible. Just heating or cooling, you should be able to go back and forth between the sol and gel states. Now, with that stage being set, we will now move our attention to an important aspect of hydrogels, namely hydrogel swelling. Once the hydrogel network is formed, because these are now water swellable networks, if you will, you can now place them in water and you can swell them to equilibrium, and that drives their physical behavior. And in the swollen state, a large part of the water may be bound to the chains themselves. And in the swollen state now, because the network has sort of expanded, so to speak, solutes can diffuse in and out, and as should be obvious, the swelling can affect the diffusion of molecules and mechanical properties of the network itself. Now, a couple of terms to look at before we dive into the thermodynamics of this process. First thing is to understand what a relaxed state is and what a swollen state is. So, relaxed state in the context of hydrogels simply refers to the state post curing, that is post cross linking, but prior to swelling. And the swollen state is the equilibrium state after complete swelling in a solvent. In this case, it is water. And of course, as we have seen earlier, junction here refers to the covalent crosslink point between two polymer chains. And from a structure perspective, one important question to ask is, how do we think of molecular weight for or molar mass for a hydrogel? Earlier, when we have seen linear or branched polymers, we saw that you can now think of molar mass or Mn or Mw. We have seen a couple of different varieties of those, which simply refers to the average degree of polymerization across the chains. And because you have individual chains, you can now, for example, in Mn, you can count across chains and average them. But in the case of a hydrogel, now it is a bit more difficult to imagine, because in some sense it is essentially one big large macromolecule. You can go from here and trace, your way throughout the network, right? So, how do we even understand what molar mass is for a hydrogel network? And for that, we are going to resort to something called a MC, which is unique to hydrogels, which is the average molar mass between crosslinks. So, shown here is that process of swelling, where you have this relaxed state post curing on the left hand side, where the blue dots represent the crosslink points, and you see this would be what you would call the mesh size or the average mesh size or the molecular weight between crosslinks. And in the swollen state, you have this, where the gel has sort of swollen and the distance between the crosslinks has increased. So, this is now one way to start thinking about hydrogel microstructure or network structure, and MC is a very important network structure because it directly relates to mesh size, which is the average distance, if you will, between crosslink points. And mesh size is in turn important because that is going to affect how big of a macromolecule or a biotherapeutic, for example, can be loaded into the hydrogel and when will it release based on the swelling behavior, right. It is also important for encapsulation of biological moieties. It is also important for the encapsulation of cells, and a whole host of applications. So, the two structural parameters that we will focus on in this lecture are MC and mesh size as shown here, and they are both related. Our aim is to relate this microstructural parameter to the swelling behavior. That is the goal of this lecture. Now, from an experimental perspective, you can have a cured or a relaxed gel and a swollen gel, and you can quantify two parameters. One is a curing ratio and a swelling ratio, and you can have both weight curing ratio and volume curing ratio. Weight curing ratio is simply weight of the relaxed gel over weight of the dry gel. Volume curing ratio is simply volume of relaxed gel to volume of the dry gel, and you can go back and forth based on the densities. And one important aspect to note here is the volume fraction of polymer in the relaxed gel given as Phi2 sub r is 1 over the volume curing ratio. Now this Phi2 should remind you of the volume fraction that we have seen as part of the Flory-Huggins, which is going to show up in just a minute, but this is one way for us to understand what the volume fraction of polymer in the relaxed gel is based on the volume curing ratio. Likewise, analogously, you can also define similar parameters for a swollen gel, where weight swelling ratio is just the weight of equilibrium swollen gel in water to weight of dry gel, and volume swelling ratio, which is given as capital QS, is volume of equilibrium swollen gel to volume of the dry gel. And analogously, you can also define volume fraction of polymer in the swollen gel, which is Phi2S, which is 1 over QS. So note here that Phi2R represents the relaxed state post curing, Phi2S represents the swollen state post swelling. That's an important distinction. It's an additional qualification we have had added to Phi2 to make a distinction between the relaxed state and the swollen state, and it turns out that's an important distinction to make as we will see later in the Merrill-Peppas equation. So now we can ask, how does the hydrogel swell in the presence of water, and what are some conceptual thermodynamic ways to think about hydrogel swelling. Now imagine that there is a covalently cross-linked elastomeric network. The thermodynamic swelling contribution due to water diffusion, water is going to go inside, is countered by the retractive elastic contribution of the cross-linked structure. And as we have said earlier in this lecture, this is one reason why the network doesn't dissolve in water, but it swells. So water enters the cured hydrogel, and that's going to lead to swelling of the hydrogel in the presence of water, and the covalent crosslinks prevent dissolution, but will also exert retractive forces in the other direction. So that's what prevents the hydrogel from swelling forever, right? And equilibrium is attained, meaning you can actually think of an equilibrium swollen state for the hydrogel at a particular solvent at a particular temperature, when the two forces, one driving the water inside and the other exerting retractive forces from the network, are balanced. So if you have to formalize this a bit more, these are the two factors that compete. One is the osmotic pressure of polymer solvent system due to the solvent entering and associating with the chains, and this is given by the Flory-Huggins equation. And as we have seen earlier in Flory-Huggins in lecture 16, there are two contributions. One is the entropic contribution, which will favor mixing. The other is the enthalpic change due to chain solvent interactions. And if you recall, we looked at the chi parameter, which is the Flory parameter, that tells you something about how favorable the interactions are between polymer and the solvent. In addition, in hydrogels, you also have this retractive elastic forces exerted by the cross-linked chains as they are swelling. So if you look at this picture again, this is the relaxed state post curing, and as the water enters, placing this in a large bath of water, and the network is starting to swell because water is now getting inside the network, it will not keep swelling forever. It will keep swelling till the point when the two forces are balanced. And from a free energy perspective, one can think of the total free energy change occurring in this process as a combination of change in mixing free energy given by the Flory-Huggins and the elastic free energy given by the theory of rubber elasticity, which we have not looked at in this course yet, and we will not be looking at the details either, but I will give you a reference for it in just a bit in case you are interested in looking at the background for the theory of rubber elasticity. Essentially what we are going to say in this limited context is there is an entropic change in the network as the chains get stretched, and that decrease in entropy becomes unfavorable beyond a certain point, which leads to the chains wanting to come back to their original position. And like I said, from a free energy perspective, you can have delta G mix plus delta G elas, which is the mixing free energy and the elastic free energy. And at equilibrium, when there is no more solvent that goes in, or the amount of solvent that goes in and comes out is balanced, then free energy has to be minimum, or the chemical potential of water in the bath and the chemical potential of water inside the gel should be the same. Another way of saying it mathematically is delta mu mix plus delta mu elas should be 0. Now what we will do is quickly take a look at some expressions for the mixing term and the network elasticity term, and then set them equal to each other, and then we will come up with the Flory-Rehner Merrill-Peppas equation. The mixing term is not new to us. We have already seen entropic and enthalpic effects of solvent polymer association. This is simply the Flory-Huggins equation. So if you are not familiar with this, now would be a good time to pause and recall some of the concepts we have seen both in solution thermodynamics in lecture 15 and in the Flory-Huggins equation derivation in lecture 16. So we are going to take this equation for granted here, which we have already looked at. One important point to note here is in this case, in a hydrogel network, the network itself does not contribute to entropy of mixing. So these are the entropic terms, this is the enthalpic term. In this case, the network itself is one giant macromolecule. So it is entropically, it is configurationally constrained. So it is not going to contribute anything to the entropy. So that term drops out. So this now becomes simplified to this term or this expression. Now because we are dealing with chemical potentials, all you will have to do is differentiate this with respect to the number of moles to get an expression for mu. And the way you would do it is simply differentiate with respect to N1, where this is due to the quote unquote dilution of the network because of water entering, where the subscript 1 represents the water or the solvent at constant temperature, pressure, and N2 for a fixed number of moles of the component 2, which is the polymer network here. So delta mu mix is given by partial of delta G mix with respect to N1 at constant Tp and N2. Again, this is an expression that we have seen in solution thermodynamics in lecture 15. So if you do the math, what you will end up getting is a nice expression for delta mu mix, which is RT times ln of 1 minus phi2s, which is something that we saw could be related to capital Qs. Phi2s is simply 1 over Qs, which you can obtain from experiments through swelling, plus phi2s plus chi12, which is the Flory parameter, times phi2s square. So that is the expression for delta mu mix. Now you can next look at the network elasticity term, and here we note the entropy loss in network due to stretching resists swelling. Essentially, as the network keeps swelling, the number of arrangements that are possible starts becoming lower and lower, and that is not thermodynamically favorable. So that is going to resist swelling, and you will see that that is going to have its own consequences for how much a hydrogel can swell. Now the expression for the delta mu, the elastic contribution, comes to us from the theory of rubber elasticity or the Flory-Rehner theory. With corrections from Merrill-Peppas. Now this is not something that we are going to look at in any detail in this lecture, but if you are interested in how this expression is derived, I would encourage you to look at this reference, which provides some details of how this expression can be arrived at. What we will focus on here is understanding physically what this expression really means. So you see, this expression gives you a way to relate the network elasticity term, that is the change in free energy, to the volume fraction of the polymer in the relaxed and the swollen states, mc, which is the molecular weight between crosslinks, mn, which is the molar mass of the initial polymer that you begin with, and V1 sub m represents the molar volume of the solvent, which is fixed for water or any solvent that you are using, and nu2, which is the specific volume of the unswollen polymer, which is also fixed based on your experiment. Of course, it is going to depend on temperature as well. Another important structural parameter related to MC is this cross-link density, kappa sub x, which has to do with which relates to MC as 1 over nu2 times MC. So, if you have MC, not only can you understand hydrogel swelling behavior, you also can access the cross-link density. Now, putting 2 and 2 together, at equilibrium we set these terms to the sum of these terms has to go to 0, or one has to be balanced by the other, and if you do the algebra and rearrange, what you will end up getting is this very famous Flory-Rehner Merrill-Peppas equation, which now relates the structural parameter MC, which is the molar mass or molecular weight between crosslinks, to swelling, and that is a very, very important idea, because what you can now be able to do is from swelling experiments. Remember that Phi2R and Phi2S are accessible experimentally because they are related to QR and QS, as we saw earlier in this lecture. Now, based on measurements of capital QR and capital QS, you can access Phi2R and Phi2S, and if you know the molar volume of the solvent and nu2, and if you know the molar mass, the number average molar mass of the initial polymer chains, you can actually determine MC from this equation. Now, this is a very important powerful equation because MC is a network structural parameter, and this equation relates that to something that you can actually measure experimentally, which is Phi2S over Phi2R. Now, one question you might have is, what is the role of temperature here? Temperature does not seem to explicitly appear anywhere in this equation, and intuition should tell you that temperature should have an effect on this. If you carefully look at and inspect this equation, you will see that the temperature effects are embedded in this term here, which is the Flory parameter, which depends on temperature. So, temperature effects are intrinsically enabled or embedded in this one term, which is the Flory parameter. Now, from a qualitative perspective, you can imagine that as the Phi2R decreases, swelling is going to increase. As the molecular weight between crosslinks increases, your swelling is going to increase, and as chi12 decreases, you have better polymer solvent interactions, so swelling is going to increase. So, those are all some direct outcomes of the Flory-Rehner Merrill-Peppas equation. Now, the Merrill-Peppas corrections are primarily accounting for both the fact that these hydrogels are formed in the presence or cured in the presence of a solvent, meaning the base state for the Merrill-Peppas equation is not the dry state of the gel, but the relaxed state. That is why we are interested in Phi2S over Phi2R, where the base state is the relaxed state where the hydrogels have been cured in the presence of a solvent, and the Merrill-Peppas also accounts for non-idealities such as loops, free dangling ends such as those that we saw at the beginning of this lecture, which will not contribute to network elasticity. So, those will not contribute to the restorative elastic forces, so that has to be accounted for. So, the Merrill-Peppas equation accounts for all of these things. So, in summary, the power of this equation comes from its ability to relate a physically measured property, which is physically or experimentally accessible, to a network structural parameter MC, and through MC one can now determine crosslink density kappa x, as we saw on the previous slide, It is also related to mesh size and the scaling is to the 0.5. Mesh size scales as MC to the 0.5 in some special cases at least. And that is important because mesh size, which is again something you can physically visualize, will control the ability of the hydrogels to be used in a wide variety of applications. For example, in drug delivery, mesh size will control the size and diffusion of biomacromolecules of therapeutic proteins through the gel. In tissue engineering, the mesh size will dictate cell infiltration and nutrient transport. And of course, in high performance applications, biomedical applications, the mechanical properties are also impacted by the mesh size. Typically, a smaller mesh size will lead to stiffer gels. So you see, the real power of this equation, it is a very powerful equation. The real power of this comes from its ability to relate an experimentally accessible or a measurable quantity such as Phi2S over Phi2R. If you have that, if you have access to Phi2S and Phi2R, and if you know some constants related to your specific polymer solvent system at that specific temperature, you can now access MC. And that is an important network structural parameter which directly relates to mesh size, which tells you something about how these hydrogels can perform in these applications. So again, structure, MC, property, swelling or stiffness to applications such as shown here. So that same paradigm continues here as well. So with that being said, we will quickly look at some process property performance relationships in the context of hydrogels. And we will first begin by listing some types of hydrogels that are popularly used in biomedical applications and in the clinic. So some examples of anionic natural polymers include alginate and hyaluronic acid, which we have seen in quite some detail in the previous lecture. Cationic polymers include chitosan and poly-L-lysine. Chitosan is again a polymer that we have looked at in detail, where we saw that the hydrogels based on chitosan can be used for hemostatic dressings. You can also have polymers such as dextran and agarose, which are not per se charged. Agarose, as we saw earlier in this lecture, can undergo physically driven thermal gelation. Of course, depending on the functionality, the acrylate group, you can have photocross-linkable synthetic polymers. And all of these are very important types of polymers that are used for hydrogel preparation in biomedical applications. Some examples include, we saw earlier that PEG or alginate can serve as blank slates. So if you form these hydrogels using polyethylene glycol or alginate, intrinsically they are not going to elicit specific cell responses. But that also becomes useful because now they serve as blank slates, which means you have an empty canvas now onto which you can functionalize and then study specific biological responses in controlled in vitro microenvironments. So that is what we mean by controlled interrogation here. This can help you clarify mechanisms, for example. You can also enable cell attachment through the grafting of cell adhesive ligands such as RGD, which is a peptide sequence that cells can recognize. So you can now covalently attach to the hydrogel network these RGD sequences onto which cells can attach. Of course, based on the mesh size, these hydrogels can also promote diffusion of biomacromolecules, and we will look at some quick examples of that when we look at stimuli-responsive hydrogels in just a while. And because of the water holding property, they are also suitable for wound healing, and hydrogels can also be used for anti-fouling applications, as we have seen earlier, for specific reasons that we will not get into right now. They resist protein adsorption, so they can serve as anti-fouling surfaces. So you see, both the canvas available for hydrogel preparation and the ambit of applications are both very large. Just to reiterate this process structure property performance paradigm, we are taking the specific example of PEG diacrylate, where we have the diacrylate functionality here. The double bond can undergo free radical polymerization in the presence of free radicals and in the presence of UV light. So you have this precursor or pre-gel monomer solution in the presence of photoinitiator and ultraviolet light can undergo this polymerization to form a cross-linked network like so, where these dots again junctions represent the cross-link points. And this is something we've already looked at in some detail in both molecular structure in lecture 7 and chain growth in lecture 11. But what we want to highlight here is the effect of precursor concentration and molar mass on the cross-linking density, mesh size and swelling. So these are factors or parameters that you can change or is within your control. So the precursor concentration, the concentration of the precursor or the pre-gel in solution and the molar mass of the peg itself. So the N here, both of these are under your control. And once you know how both precursor concentration and the molar mass, so Mn here, which should be related to the Merrill-Peppas equation, dictate and decide how Mc is dictated, then you can immediately from there derive how cross-linking density is going to change, what is the mesh size and what is the swelling behavior. All of those can be obtained. So you see, it's a beautiful set of relationships that exist between the structure guiding the property, guiding the application, function and performance. So in closing, we will look at some advanced types of hydrogels which are particularly important for biomedical or clinical applications. And as a example, we will look at thermoresponsive, enzyme responsive and pH responsive hydrogels. So these are a class of hydrogels essentially that respond to a particular stimulus from within the microenvironment. So the first example is a thermoresponsive hydrogel. We already saw that you can have HPMC and agarose undergoing thermally driven gelation. Here we revisit our familiar example of poly-NiPAM, poly-N isopropyl acrylamide hydrogels that are that exhibit an LCST, a lower critical solution temperature. So essentially below the LCST, that is when you are below that 32 degrees which happens to be the LCST for this polymer, they have both hydrophilic and hydrophobic moieties, and the hydrophilic moiety in the amide groups can very strongly hydrogen bond with water, and that leads to a decrease in the enthalpy which is favorable from a free energy perspective. But the isopropyl hydrophobic groups, which also exist in poly-NiPAM, don't want to interact with water at room temperature. So what will happen is water will form a caged structure around the isopropyl groups. Now that cage structure because of higher ordering is going to lead to a decrease in entropy which is not favorable, but the enthalpy reduction occurring from the hydrogen bonding of the amide groups with water is going to supersede the loss in entropy occurring due to the water forming the cage structure around the isopropyl groups. So this will form, this will go into solution at room temperature. Now if you heat it beyond the LCST, this undergoes a coil globule transition where at higher temperatures this is no longer favorable and the hydrogen bonds are broken, and water also is released from its cage structure. So now you will have hydrophobic associations just as we saw in HPMC, that leads to collapse of this network expelling the water. So in some sense one can think of the network being hydrophilic quote unquote below the LCST and hydrophobic above the LCST. What we mean by hydrophilic and hydrophobic is which interactions dominate. The hydrogen bonding interactions dominate at room temperature or below the LCST, and the hydrophobic interactions leading to collapse and expelling of water dominate at above the LCST, and it so happens that body temperature is 37 degrees which is above the LCST. So one can think of preparing injectable hydrogel based systems derived from poly-NiPAM for various applications, because it will undergo that sol-gel transition as you inject it. Another example is that of enzyme responsive hydrogels. So these are networks that are sensitive to some enzymes present in the microenvironment. For example, we are showing 3 different versions of that here. In the first version, you have a network where the network itself is sensitive to, there are groups in the network that are sensitive to the to a specific enzyme, let's say in the microenvironment in the body, and these red dots represent the biological therapeutics that are embedded or impregnated into the hydrogel. And in the presence of a particular enzyme like so, these chains can undergo scission, thus opening up the network, leading to release of these molecules. Another version of this could be where not the entire network is enzymatically sensitive, but only certain regions are enzymatically sensitive, such as shown in red here. So this, you can imagine, will lead to more controlled and more specific scission points, where only these points will cleave in the presence of an enzyme, and the therapeutic molecule loaded in will release in a more controlled manner, for example. You can also have an enzymatically sensitive linker. So in this case, the hydrogel retains its structure. So in the former two cases, the hydrogel itself will disintegrate because of chain scission. In this case, the hydrogel is not enzymatically sensitive and will retain its structure, but the therapeutic molecule is now linked, covalently linked to the hydrogel network through these red covalent linkages, which will specifically undergo chain scission, leading to release of the therapeutics. So these are some ways to think about enzymatically sensitive or enzymatically responsive hydrogels. The last category are pH responsive hydrogels, where again you can have two categories based on the pK values and based on the type of charge present in the hydrogel. You can have a cationic hydrogel and an anionic hydrogel. Essentially, you have to be able to relate here the presence of charge to swelling. So the swelling is governed by charge on the hydrogel. So a cationic hydrogel in a basic solution is unswollen because of the presence of hydroxyl ions. Now when you put it in an acidic solution, because of a large amount of protonation, it is going to lead to repulsion, electrostatic repulsions that leads to swelling. So you have protonation under acidic environments, which leads to electrostatic repulsions because of a large presence of positively charged groups right next to each other. That is going to lead to electrostatic repulsions, resulting in a swelling of the network. Likewise, you can have the opposite for anionic hydrogels, which will swell in a basic solution, again driven by electrostatic interactions. And you can imagine that this change in pH can be very well utilized for the swollen network to release specific bioactive molecules only in the swollen state, right. So you can imagine that this can have some direct applications in oral drug delivery, because the stomach and microenvironment is acidic. So that can have implications for when this biomolecule will be released and when it will not be released. So with that, we come to the end of this lecture, and my hope is you've got a good sense of what hydrogels are from a conceptual perspective and from a thermodynamic and structural perspective. And we've also looked at some key paradigms for hydrogels in the context of structure, property, function and performance relationships.